So it's given graph, given two graphs. And which represent as G1 equal to V1 E1, right? Okay. And then so some graph they also hold for W. And so depending on the problem formulation, the author treated. So some graph they do have the W and corresponding to the weight in the edge, right? I don't know why this is not easy to write. This is to G2 in equal to V2 and E2 W2. And then so alignment corresponding to we wanted to find. And here another condition, let's say V1, the size of V1 is smaller than V2 or equal to, right? So you just say the size may be different. And so just make sure they order in these two graphs in this way. And this network alignment, which corresponding to find a mapping. And when we call mapping corresponding to, we want to find a function. And this mapping function corresponding to map V1 to V2, right? And this is connection. V1 is one connection, V2 is one connection. And we want to find this kind of function. And then this network alignment, you find this function is not enough. And usually find this function such that to maximize the similarity of two graphs, and which one represented us as the similarity of the functional similarity of mapping pairs. Plus this else, plus the topology structure similarity corresponding to the influence topology. So this topology corresponding to just like the shortest path. And so one vertex connecting with another vertex can through multiple step relationship, not multiple step neighborhood relationship, and such that in the graph and one vertex, and this vertex will influenced by adjacent vertex, and adjacent vertex influenced by another adjacent vertex. So when we check this graph with another graph, I use different shape to represent different graphs. So in that case, it is you want to make sure not only the object are similar, and also the structure of this one is kind of similar. The structure. This structure is not exactly to say it can be represented. Structure could be represented different way. Can be represented by edges. Can be represented by the influence came from the another vertex, corresponding to importance of this vertex, can be represented as different ways. And some of people they treat as the centrality. centrality. Take a look at the centrality of each nodes, and take a look at the role of each nodes, and to decide the topology similarity. So they have a different way to do that. Now, this is general network alignment, right? So corresponding to, you want to find the mapping, and at the same time, you want to make sure that maximize the similarity score, right? You want to have some similarity score, want to, to maximize. And so this depending on how do you define the scores. And this reason came from different paper and different algorithm, right? So now I wanted to specific on the Pinalog. Okay, so now we talk about the Pinalog. In the Pinalog, the author, the claim, and one of the claim it is they say that in the specific. So first I talk about the underline. Let's just say underline assumption in this method. So the authors, the paper authors, they think about the PPI network. And the PPI networks, let's use PPIN to represent that. And they said PPI networks consist of many communities. They call it communities. And corresponding to, let me show you. So for talk about communities, in this time I need to go to this paper. So because they already have picture here, right? And also we can go to the specific, let's see. Okay, first I checked here, right? So this is one graph. Take a look at this one. The right one, can you see my moving mouse? Yes? Yes or no? Deepika? I think it's muted. Deepika? Can you see the moving mouse? So the right one here corresponding to one network, and this one corresponding to another network. All right? So let me draw here. I may not draw exactly the same as what they do have. Okay, so this is one network, and the second network, which corresponding to, this is G1. And we put them in the same color, right? Let's say we use different color. And this is the another graph. Right? So this is G2. The worst thing about in the PPI network, they consist of many communities. And these communities corresponding to what we mentioned, connected, which corresponding to another one, corresponding to strongly connected components. Okay, so let me write down here. What is community, right? So this is corresponding to strongly connected components. And even more than this kind of strongly. How strongly could it be strongly, right? So when this is a community corresponding to, this is corresponding to in this component, every two vertex are connected. Directly. And this corresponding to one of the term in this paper dimension. And this also corresponding to clique. This is one of the specific graph people name. It's called clique, C-L-I-Q-U-E. And clique corresponding to, in this graph, every vertex has direct connection. And every vertex, just like think about it this way, right? You have three friends, and these three friends actually, every two, they are friends. So corresponding to the image like that. Here we'll talk about community, right? So for example, if you have three nodes, corresponding to, for example, you have three people in a group, right? And every two people are friends to each other. So this is this is called three node clique. Some people just say this is a three clique. And take a look at this one, right? So if you only have this one, it's the four node graph. This is not clique because with a clique corresponding to every two nodes, they are connected by one direct edge. So you can see this has the edge, this one has edge, this one. But we do not have this one and this one, right? If these two are linked, in this case, this is the people call four clique. People just ignore the load and just say this is the four clique. This one can also, you can ignore that. You can ignore this one. It's called three clique, four clique. And also five clique, right? So take a look at this definition. Clique is one of the type of graph. It's also the complete graph. And corresponding to every vertex, every two vertex, they are adjacent connected. Adjacent connected, which is explicit connected. It's corresponding to one-step neighborhood relation, and every two vertex has this one-step neighborhood relation, right? So this is the five clique. In this author, they claim in the PPI network, and since it's corresponding to protein-protein interaction network, and such that in this network, there appear many protein complex. Another term in this paper dimension, the protein, sometimes you feel confused for some term. So let me explain. So when you take a look, when they talk about the protein complex, which is corresponding to many protein, they are interact in this way, they're together, complex corresponding to a group. They're grouped in some way. And such that once they group, and you can treat them just like this clique. So in this paper, they say because there are so many protein complex, and such that the underline, they do have many this kind of cliques, right? And for example, in these two graphs, so they say this one is a clique, right? Let's say this is a vertex. Let's say this is a 1. Let's give the name 1, 2, 3, 4, right? 5, 6, 7, 8, 9, 10, 11, 12, right? And so in such that the 2, 3, 4. This one form what? Form 3 click. Right? And then take a look at this one, and 6, 7, 8, 9, which is a form 4 click. 4 click corresponding to 4 load click, right? So then, and so you can see here. And also in this one, if they never give them different, just arbitrarily give the load index, right? So maybe not exactly, we just want to simplify that. We do not give the name of a protein. But you can imagine it is every sky, they could be corresponding to one of the object, right? Any kind of object you are interested in, right? So in this case, also this one, I think we missed one link is here. It's one link, right? And then so in this case, they also have, in this one, they also have, 3, 4, 5, which is corresponding to this guy, right? This one, right? This part. And which is corresponding to 3 click. As you use 3C, that's save our time, right? And then in this side, you have 6, 8, 7, 9, and this go to the 4 click. Right? And then so in this paper, and they said, this one, this is 1 4 click. This one, can you see this one? So this is the 6, 8, 6, 8, 6, 8, 9, 10, right? This is another 4 click. Okay, can you see that? This have this one, right? You also have this one, right? Okay, so this is the author's idea. They said, okay, since the protein-protein interaction, they do include the many kind of this protein complex, and such that when you read this graph, you want to find out these different cliques. And if once you find these cliques, you use these cliques as the seed. You use this clique as a seed. You mapping these cliques. You mapping these cliques in the one graph, mapping to the clique in another graph. And you use this mapping as the seeds. Then you extend it out. And to see what is the other specific vortex can be mapped. And such that you can imagine if they first map the cliques, right? Map these different cliques. Then in such a way, they can partially fill in this function, right? And after that, it is they exploit out. To exploit out to see the labels, the related labels, how they map. And such that they want to find out this function. And also make sure this maximizes the similarity score. Now let's take a look. What is this similarity score the author treated, right? Can you see, right? The similarity score. How this author judge the similarity score. And this similarity score, is go to here, right? First, they have different functions. So I list this function, then I list the steps. And then this will be mapped to this the paper talk about. Okay, so the first, you have different functions, right? Okay, so first let's check any pair of vertex. So let's say this is the VI. This is the VJ, right? Let's use the same as the paper mentioned, and treat this one as the AI, right? And this is the, let's use a different color to represent. Let's see one of the vertex here. This is 9 is the index. Let's say this is the AI, right? And let's just randomly use something here. This is the BJ, right? BJ. So for any this kind of VI and BJ, let's see here, right? For any, right? This corresponding for any AI. For any AI belong to this VAI, belong to V1, right? And this BJ, okay, I maybe just ignore the writing part if that's not so good, okay? So is it belong to V2, right? And then so similarity between them, and the author consider two similarity score, and they combine them together. So the similarity have different similarity. Use S to represent the similarity, right? And I use this one, S. In the paper, they just use S. And I want to use the same, right? Same corresponding similarity. And the same on the sequence side, right? Because each protein, we said we'll talk about the sequence alignment, right? So this is the AI. And this is the BJ, right? So this sequence alignment, the author, what they do, they use the, okay. For this sequence alignment, they also use what we mentioned, the sequence alignment. And the specific tool the author use is sequence alignment score. So this is exactly as what we talk about, the longest common subsequence, right? So this is used, the tool is BLAST bit. Since it's BLAST bit, and such that the author treat this one as SAI. Okay, this is go to, let's use this one, right? This one, right? This tool. So you got this tool, use this tool. Let's use the S. Use S to represent this tool, right? And this tool, what they get the number, and with BJ, and then divide by, this is normalized score, S, AI, AI. And then times S, BJ, BJ. Okay, so you may ask why they're divided by these two, because different sequence, this is the one protein from here, another protein from here, right? So this protein, you treat them, they have different, just chemical compound. And this chemical compound can be represented in the sequence, and it can be represented in this, first structure, first type of structure. They could also represent as the, third dimension structure. This is the fourth dimension structure, right? To show that is the sequence. And then, so since the sequence, the length is different. And when you compare the different pairs, and since the length is different, and such that this is normalized, you treat them as normalized sequence alignment results. Normalized based on the length, right? So this is the first calculation. And the second calculation, which is based on the function set. And for this one, I want to use that it is the function. For function, I use the FUN to represent the function of AI and BJ. For this part, most of students may be very confused about that. The reason it is here. In the paper dimension, I go to the paper to show you. And in the paper, okay, so take a look at this part of the code, this part of statement. Let's make it bigger, right? So in this one, it's talk about use GO terms. Many of our students do not have idea what is GO term. GO, it is corresponding to gene ontology. This corresponding to the let me draw here. Just be well. This corresponding to this part, right? Corresponding to this part. And then so I go to here and demonstrate to you. This is from the function perspective. The function of protein, AI, and BJ, right? And how do you get this function? How to say how similar this function could be. And so each protein, they have one specific. People use ontology, people use the web semantic, right? So if you do not heard about the ontology, you may heard about, if you I eat some spicy food, so this reason a little bit cough. Okay, so don't worry. And then so how to represent the function of objects, and just like what is the function of the tables, what is the function of the books, right? So when we were little, we just started to learn the language, and our parents teach us, this is a book, this is a cell phone. And then so we recognize all the books have the same kind of function, right? All the table has the same kind of function. And later, once the people talk about, I will give you a table, then you know what is the table could be, right? So this corresponds to every objects can be cast into some categories, right? So this is corresponding to the also called the web semantic, or you can treat them as the ontologies. Corresponding to manager is the goal, it is here, manage the knowledge of objects. Okay, this is for manage the knowledge of objects through use this ontology, use the semantic web of, right? And then so specifically what corresponding to, and corresponding to, they put the objects and in a different class. So they have a root class, right? The root class. And then they have a different cast into different class 1 and class 2, and this class. And then class 1 and put into different another, class 3 and class 4. And use this structure just like your book chapter, right? Just your textbook. We use categories to organize the specific knowledge, specific chapters. And the same thing here. In the real life, we use the classification and use these people also call semantic ontologies, and because it's beyond classification. It includes classification and also includes some logical specific logical relationship inside of here. So it means this is beyond classification, include classification and also beyond that. So just be well off when you take a look at ontology, when you take a look about the semantic function or semantic definition, all this corresponding to this is just like a tree structure. And finally, what you have the AI is here. And maybe you have the BJ is here, right? And then, so in this ontology, because the manager, the knowledge of objects, and it's specifically from the function perspective. And since it's from the function perspective, and such that the words think about to calculate the function similarity for AI and BJ, and what they can do, it is so what they can do, it is they can see how many vertex belong here, how many specific protein here, how many protein here. And this is corresponding to, in the paper dimension, the reality. Take a look at this one. Yes, here, right? So the similarity it depends on variety of the terms in the annotation database as the distance in the ontology, right? So this is the same as what we discussed here. When you want to compare the function of A and Bj, you check which common class they belong to, and how rarity and this could be, right? How rarity corresponding to how much chance these two proteins can belong to that group, and also corresponding to how much probability is A and Bj and they happen to be in the same function group. It's called rarity, right? So and such that, so what they do it is they check, since AI it is one protein and which is belong to specific class, and such that what they do it is they check how many specific and how many vortex is corresponding to how many vortex belong to this group, in this group, right, which they stay, and such that, and they want to check the similarity between the proteins in this group. This should be 5, right? Let's see, it's 5, right? So they want to check how many proteins belong this group and how many proteins belong this group, and check the similarity between these two groups, because these two groups tell you all the proteins in this group they have similar, right? For example, if we many terms belong to the chapter 1, in that case, all these terms in the chapter 1 should be related better than the terms in the chapter 2, right? So this is the same concept. When you use the tree, this category classification to group the objects in such a way, the objects are in the same group are more similar, right? So this reason, this one changed to be the another specific to calculate the similarity, semantic similarity. And what they do it is they check the similarity between the two groups. And such that since it belongs to two groups, let's claim in this way, right? So let's say check the associate group. The associated group with GI, with GAI, which is equal to, we use this term to represent. So it's equal to, for example, another protein, right? T1, T2, and TK. And the group of BJ is equal to T1, that is the prime, and T2 prime, and TL prime, right? Because they are in the different groups, right? So they may stay in the same group, may not. It really depending on. And make it as general as possible, we write in this way. And such that, based on these two groups, we could make a matrix. And in this matrix, which corresponds to what we have, this part is GI, right? Corresponding to this is T1, T2, and TK, right? And this side, this we talk about GBJ. And this is T1 prime, T2 prime, and TL prime. Right? And then such that you can calculate the similarity score between these two proteins in the different groups, right? So you have a score, similarity score here. You can use the sequence similarity score to put it here. And such that for each row, you can have a row score, the row similarity score. And corresponding to this protein, how similar they are with this one. And usually, this row score, let me write it down here. This row score, you treat them as the average. As average of all the similarity of this one with the sequence here, right? Corresponding to the average of the same seq and Ti with any vertex. Ti as any one, right? As T prime belong to GBJ, right? Can you see? It's just a little messy, right? So just be aware of that. So, this is just one of the way. And in your site, you really can update this calculation. This is not a perfect calculation. But the most important, this paper, they want to sell is they do not want to sell this part. They want to sell the idea. It's communication, it's community-based solution, right? So this is what they the good thing in this paper. And so this is T belong to GBJ. Okay, and then also you can get the column. So this is corresponding to rows. This is row same score. You can also get the column. Column is what we call column same score, and this is equal to average of the same seq of what, and of T belong to GAI with, for example, TJ prime, right? So for example, this is the this is TJ, this is TJ, right, prime, right? And this is the TI row, for example, right, TI row. So in such case, this is the row score similarity. This corresponding to when you check this functional similarity of proteins, you check the group similarity between this AI belonging to, right? AI belong to C3 and BGI belong to C5. And the functional similarity of AI and BGI corresponding to the similarity of the classes it belonging to. They make sense, right? So this one reduced to similarity between C3 and C5. And this similarity score can treat from part from here. And such that this is equal to, so this, do I need to write it down? It's good, right? So the similarity of this AI and BGI corresponding to the same function of what? Of the ontology. What is the class? Class AI belongs to, and then so we see this is the class, and BJ belongs to, right? Okay, and then so based on this discussion and what the author, not this one, I'm trying to scroll up. Okay, so then so this is same function of AI and BJ is equal to, right? And the previous one we just discussed about that. Now we can go to specific the function here. Okay, and so also we have the function here, right? This corresponds to sequence similarity between these two proteins. And also consider both, and also consider the topology. Let's see. So this one is equal to, this one is equal to the this is equal to what? And equal to what you have the, the this is called the semantic similarity divided by maximum of row score and column score. And corresponding to this is the T, once you have A and Bj, right? And such that, so you have this matrix. And in this matrix, you got two groups. And from these two groups, is a group of AI and a group of Bj. And then so you have this matrix. And the AI and Bj maybe belong to all of these kind of things. And you get this similar score over here, divided by maximum of the row score, maximum of the column score, right? So this is the average. I know that's good. So it's clear? It's clear, right? And then, so they also think about S, the sequence similarity, S sim, we use S correspond to sim. S is AI and Bj is equal to, weighted function of sim seq AI Bj plus 1 minus theta sim function AI Bj. So this is based on the protein only in the object perspective. And later, they also think about the topology side. And the topology side. This one is not a topology side, right? It's just an object-to-object similarity. And then they talk about the topology side. In the topology side, and the author, this is a more complicated story now. Go to the topology side, and what they did, it is first. So now, first, take a look at this one, right? And to calculate this similarity, what we talk about this similarity for every two pairs, one from AI, which is belong to V1, right? And Bj belong to V2, right? And so for every vertex pair, and you can make this one, even without topology. So it means it doesn't matter how these proteins interact with each other, and you can calculate this similarity score of each pair. And then, and after that, so this is the first step, right? You calculate this one. And then also second step, it is go to this graph, right? Second graph, it is, they want to say, okay, from each graphs, first you need to find out community, right? Corresponding, you need to find out the clicks. You find out clicks. And they have specific tools you can use to find the clicks. And find the clicks correspond, want to find the subnetwork, and all the vertex are adjacent to each other, right? So, and in this paper, they use cfind. They use a specific tool. So let me write it down here. The step one. And in the step one, so let's see here, right? We already finished this previous part. In this step for the topology side, and the author find the community, right? So this one, it is identify community in each graph. Okay, so I see one student asked a question. Let's take a look. Kasika. Oh, I see. Kasika, we use the data. Okay, Sepla. So today, we have team 1. They reserve this time for paper 2. I'm sorry, for paper 1. And for your paper 2, I sent you an email. Did you get my email? So you can choose the early morning tomorrow or in the afternoon. Today, if we have time, we can go to paper 2. But it seems to take long to discuss each paper. If you give me the specific question, we answer that could be fast. But if we wanted to discuss the paper, then in that case, I want to make sure you understand all this formula. So it take time. Let me know, Sepla. 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 Yes, so I just saw your message in the chat box, and I feel sorry about that. So the team one reserved today's 8 p.m. So if we just answer the specific question, could be fast. But seems for all this discussed method, it always take time. So I sent you email already. So you just tell me you want it in the morning or in the afternoon for you and your team. So just to check that, okay? And then so in my side it is I want to make sure the people who choose paper 2 most of them can join. Okay? So in your side you just need to answer me. You want it to the 9 a.m. or 3 p.m. Okay? Okay. Hello? What do you say? I'm sorry. Your voice is very small. I can very soft. Your voice. Mm-hmm. That's good. You see, it's 3 p.m. That's totally fine. So also, by the way, do you have a contact with the people who in your team in the paper 2? Yeah, that'll be good. Thank you, Sepla. Please inform them, okay? So then we just 3 p.m. we chat, okay? So if you want to stay, you stay. If you don't want to, that's fine. Okay, thank you. Kasika. Yeah, I just noticed your message. Mm-hmm. Okay, so you use the data which the author had mentioned in the software, but during the uploading, get connection timeout. Uploading of what? Okay, I see. So yeah, I know your question. So in this paper they provided the multiple link, and so that would be better one. It is you download the software and put in your personal computer, and you need to check what they provided. If they provided the web service based, this timeout could be problem. But usually if it's in the personal computer, this should be no problem. And also, so if they have a problem, if they run, they say the software collapse. That's another story. The collapse corresponding to they may have some bugs or some configuration problem. So most likely should be configuration problem, because this paper which is published the top one by Informatics Journal. This is top 1 by Informatics Journal. In my all my publication, I do have one. I did have one paper from the Bioinformatics Journal. This is the best Bioinformatics Journal. So it corresponding to if they mentioned the software, this software should work. And so you check based on what you discuss. So timeout message in your browser, it corresponding to you use data web server. So do not use data web server. The better it is you download the data source code, run from the source code. And also we need to adapt it because we want you use the coronavirus data, use the influenza data. That is, people say the symptoms are so similar, but they are different underlying mechanism. We want to use this comparison to check how they are different viruses. Okay, so I'm sorry. Yeah, I'm sorry. Okay, good. Okay, so check that. Then if you have more question, let me know. Okay. So I think some of students maybe think what I discuss is this way is too much details, right? Right? It's okay or not? Do you want to continue or this is good enough for now? Okay, then in that case, I'll try to make it shorter, okay? So if you have a question, you can write it down in the chat box. Kasika, okay, good. Okay, good. Okay, very good. Okay, now, so now I want to make it fast, right? So, identify community in each graph using also Kasika. Kasika? Did you notice that they use the cfind? They already included in the package? Yeah. So this one should be included in the package because if they want to run, one of the steps it is they need to identify that communities corresponding to these two graphs, and they need to find out these two. For this graph, they need to find out is 3. Okay, so they should have that. You take a look at the code, and take a look at the code and take a look. So first they identify the communities, right? And then second one, and then what they do it is, excuse me, and then it is for cfind they find all these K-clicks. This is K-clicks. And this K could be usually the starting from 3, 4, 5, 6 could be corresponding that K clips, right? And then so this is after they identify the similarity scheme and they do the topology similarity set. So this is what they work now. And then so and then after that it is determine the highest score. When equivalence proteins in each community of A and community of B corresponding to this part is determined. This corresponding to this determined, right? This corresponding to map. So let's see here, right? We see this is CI, this is CJ, right? And CI corresponding to one of, I use CI to represent one of the click in the community in the graph A. This is belong to V1, right? Not, so it should be written down in this way. Okay, the space not enough. So this CI is a subset of V1. And this one is a subset of V2, right? Can you see? And then so this is the previous step. Use this tool. I'll write it down here, right? So this they want to find the community by use this tool. And then after that, in this step, so what they do it is they map in the vortex V, let's say Vi, which is belong to the Ci. Let's use not use I, let's use K. Belong to this one, and VL belong to CJ. And the map the vortex of this one to this one, right? They want to find the mapping. they want to find the best mapping of each vertex in the community 1 of A and community J in the V2. This is VL. Okay, and so this is the mapping. And this is for this step. And such that they used, in this paper, they use a specific formula to say, they say they found the best mapping function, F, and F of CIA and CJB. And this is equal to okay, so this is the mapping function, right? This is the mapping function. They want to make sure this mapping, for example, let's show you example, right? And so example here, we have 3 click of these 3 loads. We have 3 click of these loads. They map this old vertex with this vertex here. And also, they also map what you have these 3 loads in this click with the 4 click, with this 4 click, and to say how similar they are. So that means they for every pair of click, they map the click pairs. Can you see here? So this is for map the, let me write it down here. I use different color. This is for map clicks. Map these clicks. Map the vertices in clicks. And this clicks from A and B. Is from. Okay. And so this one, the score of one click mapping to another click is equal to summation of similarity. This similarity corresponding to what we have the function before, and open the map of CIA and CJB. This is open the map. Open the map here corresponding to the best mapping score. Find the best mapping score of CIA to CJB. And then you sum up all this score. And so this is for sum up all this mapping, the vertex pairs. So this one corresponding to, if I list that, corresponding to a connection of, let's say let's use V1, V2, let's use the V specific, right? That's V3. That would be better you write it down in this way. Okay, I write down this way, okay? So this is the best mapping of U belong to CIA. This is pair, right? To what you have this F function or U. And which is belong to CJB. This is what they talk about open map. Open the map. Belong to, this is belong to. And or if you would like to separate this 2F and this corresponding to, this is the best. This is, let's use F star to represent best mapping, right? And the best mapping corresponding to, and if you take a look at this example, for example, 2 mapped to 3, 3 mapped to 4, 4 mapped to 5. Or maybe it is 3 mapped to 3, 2 mapped to 4, 4 mapped to 5, right? And depending on what is give you best score. This is what they mentioned that. And also, this is the mapping pair, this mapping pairs. And this is corresponding to that, right? So if you have this kind of pair, it's P, let's say capital P, right? Capital P equal to this. And then here is corresponding to for every pair belong to this capital P. Then you do this summation. Okay, and then this score, this same score, this same came from here. Can you see that? Came from here. So let's say this is the formula. This is the formula 1, right? This is formula 1, and this is the formula 2, and this is the formula 3. And this one, it is a formula, this one, it is a formula 4, right? This is the formula 4. And it's the formula 4 here. This is same corresponding to what we have the formula 3. Okay? And then, so in this one, they calculate the community to community similarity, best map, right? And then after that, let's use this color to represent. And after that, okay. And after that, it is the author, they get the obtain the best equivalence. This is just calculate for each community pair, right? Is for a community pair. And here, this one to obtain the best equivalence of all the communities. By maximize the community scoring function, and such that is the best equivalence okay. And then so this is the calculation of F core. They treat if they find the best community, similarity map, best community map for all the communities, and this is equal to summation of F, CIA, and CJB, and such that CIA, which is a subset of V1, corresponding graph 1, and CJB is a subset of V2. This is to calculate this part is the formula to calculate the best mapping for all the communities, right? So in this case, just like in this case, right, you have 2 communities in graph 1, you have 3 communities in graph 2. And so if you count the community pairs, you have 6 pairs, right? So each map to here, map to here, and map to here. And each map to here and here and here, right? And then after that, you want to find the best mapping, best community mapping. Corresponding to here, you want to find the one of best mapping here, for example, right? Best mapping, community-based best mapping, right? And then so after that, it is you put this best mapping in the core, So this is what we have the fifth function, and also in the paper, they mentioned that in this order. And then after that, it is once you already have a core, then you go to the next step. And the next step corresponding to you repeatedly to expand what you have the mapping. So repeatedly expand vertex to vertex mapping. Based on neighborhood relationship. So in the shortest path, we talk about that, right? We say that one of the questions in the graph is reachability. Corresponding to, for example, the social network. In the social network, people A is a friend of people B. And people B is a friend of people C. So this is what we mentioned, the direct connection, the adjacent edge. And corresponding to step 1, neighborhood relation. But if we think about, because people A is a friend of people B is a friend of people C, and such A is also friend of people C. So this relationship can be transitive. This relationship can be, can be counted based on the multiple steps, right? So in that case, it's a two-step neighborhood relation. Okay, this is repeatedly. I don't know why they didn't record it. Repeatedly expand the vortex to vortex. Okay, so and then what they do it is, so they use, because here you already have this core, right? This core corresponding to, you already have a subgroup of vortex, you already count. For example, in this case, you already check the best mapping for this vortex. You already got the best mapping for this vortex. Now you want to check the labels, how labels can be mapped, right? Can you see that? So this is the idea for this step. And then what they also do, it is they check expanded mapping, is performed by considering labels of proteins in the core equivalence as the candidates for adding to the alignment. So this one corresponding to, let me write it down here, is to calculate the same similarity, that is extended map, right? Extended map of, now let's use the AI and BJ to represent, right? And AI, BJ, they, in this case, AI, BJ will belong to the vortex which is not in the core. This is 1, 5, 10, 11, 12, right? 1, 2, 10, 11, 12. This is what they mentioned, check when they expanded from there. And also they can expand it from the vortex in the vortex, which is in the core, right? And then, so this one is equal to what you already have the best mapping of AI, BJ, right? So let's just see here. This is the main step, right? Main step. And so the step of here it is for any CAI, BJ belong to core, right? Belong to core. And this A and BJ, we see the BJ, it is one of mapping function of AI, right? You find the best mapping first, right? From the based on the community, you find the best mapping. And then for every this kind of pair, you do this calculation. And this is plus, we know the finish, plus the labels, the similarity from labels. So this similarity of labels, you count it is the same, and AKBL divided by the distance of AK AI plus 1 plus distance of, this is BL with BJ plus 1. So this is for this function here. This is just say they wanted to say this because it could be multi-step neighborhood relation, and you use this one divided by that, get the average contribution of the labels. Okay, so and then so this AK is belong to the neighborhood of AI. And it could be, in the paper, they mention it is the step 1 relationship. But in the some way it is, you could use a multiple step relationship. And this is neighborhood from the BJ. And A and K and AI, AK and BJ, AK and BL, and also belong to the core, So you use this way to expand it out. And once you find the good mapping of, A and BJ to, union, to, A and BJ, And then after that, it is you change the core to be union of AI, BJ. Okay, so if you find this good mapping, right, based on this score, if you can this good mapping, you change the core, and then after that it is you go back to here again, here again, because you need to repeat this step. You repeat this step to expand it out, find the best mapping, and then so until every vortex has been, cut, has been covered, has been included in the core. So this is the last step. And so in this paper, if you want to think about how to change this one, and have one of the way it is for this similarity score, in this way, you may find that I could have a better way to do that. And so if you have a question, you can ask me, and you can also search in the internet. Another one, it is this calculation side. So the paper mentioned this one, it is the first step, neighborhood, and this is the second step, neighborhood. It corresponds to step 2, two-step neighborhood. So in your side, it is you can change this one. So this is just from the formulation part. And then in the formula part, another thing it is, you may find out in this paper, they do not use the weight. They do not use the weights in the graphs. And in many graphs, they do have the weight on each edges, corresponding to the confidence of this interaction. Now it is, how can you change these formulas and to handle with the weight, this weight? So this is something you can do in this paper. Then this is the big things you can handle with that. Okay? And also in this paper, and since this community, take a look at this one, right? And so when you find the communities, take a look at this one. And graph 2, we still have 3 clicks, 3 communities. And you may find out, and these two appear in the 2 communities. This corresponds to the communities are overlapping. Once they are overlapping, when you have used the best mapping of clicks, in some way, they may have one vortex, maybe map to multiple vortex in the G2. So this is a many-to-many mapping. This one, it is a many-to-many mapping. First is global alignment, right? This is the global alignment. And plus, this is the many-to-many mapping. It's not a one-to-many mapping, it's many-to-many mapping. And such that this may cause many problems. And they have some conflict problems sometimes. How can you find the conflicts? Okay, I think that is good enough. I think I give you very detailed explanation and also give you the hint about how to change this, how to make it your own algorithm. Let me save these notes. I will send you these notes. This is the paper. This is paper 1, right? Okay, this is the paper 1 notes. Okay, this is the Pinalog. Okay, so let me know. Do you have any questions?